Okay. Good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last day, where I started talking about applications of depth first search. So I had one more application I wanted to talk about and how we can use depth first search to solve some more problems. And after that, we're going to be moving on to our other graph traversal algorithm called breadth first search. So these two traversal algorithms, depth first search and breadth first search, are closely related to each other. They have some core ideas behind them that they get facilitated differently, but underlying them is a very similar process. Just if you think about it more from a data structure standpoint, it's really just swapping out data structures, which is it's interesting in its own right. So I'm hoping you'll catch on to this today. So, and depending on how far along we get from there, we might start talking about some graph theoretic problems beyond that, but we'll see. So anyways, the first application I promised I was going to talk to you about is pathfinding. So like I said, we can adapt DFS to solve many problems. So I'm going to assume that there's some global variable called P. It's just going to be an empty stack. Now, if you want to think about it from an OO standpoint, P would just simply be an instance variable in your class. So it's just an empty stack that's created. Now, there's several ways you can set this up. This is just one way I'm doing it here for you. So I'm going to have this stack P, and I'm going to presume that the stack is empty when I start us off. And now, here's going to be the ideas. I'm going to adapt DFS so that I'm going to use this stack to keep track of my path. Now, you might ask, Dan, how are you going to do this? Well, let's kind of go through the process of DFS, and let's see if we find anything interesting. Now, one thing I do need to make a remark about is that I want to find a path from S to T. So there'll be two designated vertices, S and T. And so this is often called an ST path. So an ST path is simply a path from S to T. So that's what an ST path is. So we're going to compute an ST path. So for example, you can see that there's an ST path. If this is S and that's T, you can see there's a path right here, right? So I'm going to show you how we're going to compute this path using a modified version of DFS. But I'm just going to use this stack to help me. So let's walk through the process of doing DFS. So recall that if I suppose I start at S, just like when I start up with U. So question. Can we implement the stack by always having a current node and the next node relevant by push and pop? Well, I'm just going to worry more about it just being a stack. So I'm not going to worry so much about the underlying implementation of the stack. But most certainly we could have conversations maybe after class about maybe specific kinds of stacks that might be more appropriate over other ones. But I'm just gonna, I just care it's just a stack. It could be any stack. So it could be a linked list based stack. It could be an array based stack. I don't care. It's just a stack. So anyway, so when I start up DFS, what I do, remember I mark the vertex and then I start looking at my neighbors, right? But I do this over the incident edges. So what I'm going to do is I'm going to start by pushing S onto the stack. In this case, S is A. So I'm going to push that onto my stack. Just like, you remember when we talked about how I journey through the labyrinth, right? Dance Magic Dance. It's an obligatory thing to say. Ignore me if you don't understand that reference. If I have my path that I'm venturing through, suppose that the Minotaur is here at vertex E. The idea is that I still have my spool of thread, right? So what I'm doing is I'm going to use the stack to help me keep track of where I currently am until I hit T. If I hit T, I've definitely found a path, right? But the point is I still have all this string, right? This thread. But where is that? Well, this corresponds to all my recursive calls, right? So all I'm going to do is I'm going to maintain those vertices in my stack. So I'm going to still have recursive calls just like before, except now I'm going to have this stack that's going to keep track of my thread that's going through the pathway I'm exploring. So what I'm going to do is now I consider each one of my incident edges. So I'm going to label this edge. And now I see, okay, well, I'm going to go here because I haven't yet explored there, right? So what I do, DFS, I mark it. Now notice that I have not yet reached T, right? So I'm going to just keep going. So now I'm going to consider my incident edges. Now remember, I'm going to push, I want to think about this process as I'm exploring. I want to imagine it's like the thread that I'm exploring through here. So I'm at vertex B, and I'm going to go through all my edges again, all the incident edges here. So I have this one and this one. Suppose I go to, let's go to D. Suppose that it's D. Now keep in mind this process, we don't care about which one it is. This algorithm is completely oblivious to this. But if you implement the graph in a very specific way, there might be a specific order it always uses. For example, it might be by the indices of the vertices, by their labels, for example. That's one standard way it might happen. But for our algorithm, it doesn't require it functionally speaking. So I'm just going to label this here. I'm just labeling them for the purposes of our discussion just because they did this at DFS. And now I go to D. I'm going to mark D. I'm at D. And I look, do I have any unlabeled edges? Well, in particular, do I really have to care about the edges here? Like, you seen how last day when I was counting the vertices that were reachable from you, I didn't really care about the edges, right? The edges were not really relevant at all. I just look over the edges. So, do I really have to care about labeling the edges? Not really. Not really. What I care more about is I make sure I don't revisit a place I've already been, because at the end of the day, I want to reach a vertex. So I'm trying to find vertex T. So what you'll notice that if I examine this, well, this is already marked, right? So I'm definitely not going to go back that way from D. Instead, I'm done at D because I didn't find anything. So if I have no more options to consider here, I better pop D off the stack. And that means I'm done considering this pathway in the labyrinth. So now I wind back up my spool of thread or string, and now I'm back at B. So now I'm just going to consider this incident edge. I'm just going to keep labeling them just for our purposes here, but it doesn't matter too much for us. I'm going to go to C. I'm going to push C because that might be a part of a path potentially to T. I consider my incident edges. Now, if I don't care about the labels, I would just check one. If this is marked already, I definitely don't want to go back that way and push that onto the stack too, right? I don't want to do that because I've already been there. Instead, I'm going to take this incident edge and notice that when I reach here, I'm going to mark it. I'm going to push E onto here. And then I ask, is S equal to T? Now, in this case, what you're going to notice is that when I pull this thread, so I'm going to show you the pseudocode more carefully in a moment. When I am doing this process, notice that every single time I can actually rephrase this question in terms of myself and T. So when I go from A to E, I want to find a path from here. If I go to B, it's no different if I have a path from A to B to know how to get from B to E. So really, when I go to C, it's no different to me because I know there's a path from A to B to C, right? If I start at C and I want to go to E, I want to find a path that way. So if I'm at E and I find E, am I done? Yeah, right, I'm done. So notice here that I have found a path from S to T because I'm at vertex T, and because of me starting at this point, I had to have taken some path to get there. So you might ask, Dan, where is this pathway that you speak of? Where is this mythical path that you're talking about? Well, let's take a look at what the stack looks like. There's your ST path right there. So you got A, B, C, E. A, B, C, E. So if you want to just get the path, just pop them off this stack. But keep in mind they were going to be backwards, so you're going to have to correct that. But remember, it will give it to starting at T and work your way back to S. But anyways, are there any questions about just the idea that the stack is being used just like my thread here when I was executing DFS? And really, all I'm doing is I'm just marking vertices, and I just simply just consider any incident edges I haven't, well, I consider edges, but I only follow on them if they are not marked, right? So if we're okay with this, I'm going to talk about the pseudocode here that I have over here. You'll notice that every time I've shown you one of these applications, they're almost always stripped back versions or slightly modified. So that's a nice thing about DFS. It's very easy to adapt to solve many graph theoretic problems. Just like other graph traversal algorithms. Just like when you study trees, for example, there's many kind of boilerplate style tree traversal algorithms that you can easily modify to solve other problems. So here's an example of some pseudocode to do this. So I call it pathfind to give you two vertices S and T. And it's going to output true if there's an ST path and false otherwise. So like I say, we mark the vertex, we push that vertex onto the stack. And then I ask, is S equal to T? Well, just like when I talked about how, if I'm already here, I had to have gotten there from wherever I started. And I could re-ask the question from this vertex to wherever I want to go. And I can keep asking this question until I hit T or I don't hit T. So if I hit T, then yes, I found a path. And that means I don't have to do anything any further, right? I'm done. Otherwise, I have to consider my incident edges on given the vertex S here, which, by the way, every time I call on this function recursively, S will change to whatever I feed the first parameter. Just like when I talked about here. Like if I'm at B, I know there's a path from A to B. So I'm asking another question. Now, where's the path from B to E? So I can always I can work at it that way. And because the remainder of the path will be stored in the stack. That's why I'm using the stack here. So if it's not marked, then I just simply recursively apply pathfind with U and T. So I would just simply go one step further, just like I did over here. And I would ask it on U to T. Is there a path from U to T? If it returns true, then you know you found a path, right? So you're going to find that when you're looking at this recursively, as soon as I find that path, well, it returns true, right? So as soon as it found this, it said, okay, return true. Okay, so each one of these is sitting at that pathfind call there, and says, okay, well, now I have the result for this version of it, so I'm going to return true. I'm going to return true. I'm going to return true, and I'm done. Because all of these, because it's recursion, they're all sitting on their own call stack waiting for the result of pathfind. But yeah, so if you fail to find it at any one of the edges, that means you're effectively at a dead end, right? So that means that you have no more options to consider, so you just pop that node or vertex off the stack, then you return false, because you know that going from, for example, D to E is going to be a failure if I've already visited all of this. So I want to go from A, B, D. Is there any way from A, B, D to E? The answer is no, right? Because I would have to go back through B. So are there any questions about that? So this is one way to compute a path between two vertices. So if I want to go from S to T, this is one way I could compute one. But the one thing I really want you to pay notice to is just the pattern. Notice that a lot of this is just DFS with just a little wrinkle change on it. So if you were to analyze the running time of this algorithm, it's almost identical to the one I did last day. So it's a feature. It's wonderful. So are there any questions before we proceed to talk about another property that DFS has? Are we all good to go? Give me 2 thumbs up if we're ready to go. Wonderful, wonderful. So why don't we go over here? I'm going to talk about an interesting property that DFS provides us. And these graph traversal algorithms often have lots of nice properties like these. They're very helpful for designing algorithms for problems. So let's talk about one of them that I think you might find interesting. So let's talk about let's talk about the concept of what we're going to call a DFS tree, a depth first search tree. So, do you recall that when I call DFS on a vertex U, it visits all the vertices and edges in a connected component with U in it, right? It goes to all the vertices reachable from U, right? So, if you think about it, we had this interesting thing that happened. Remember, we had this labeling process where we labeled edges by two different kinds. Can somebody remind me what the two kinds of edges were in DFS? What were they? Let's see. Yeah. Well, we have, no, I'm not looking for those. There's two. Remember, I called them black and red last day. What were they? For DFS. They were black and red. So, for example, last day we seen an application where we detected cycles. And they were, yeah, there we go, forward and back edges. Yes, very good, very good, very good, very good. So, those edges actually play an interesting role in how we explore this graph. So, suppose that I did DFS from A here, at the start here. Now, suppose I were to apply DFS. I might go, so remember, I marked this vertex. I go over this incident edge. I would label this a discovery edge. I mark this vertex. I consider my incident edges, right? I label this a discovery edge. Same idea here. I might consider this edge. I label that a discovery edge. I mark this one. Notice that I'm going to have some of these that are not going to be discovery edges, right? Some are back edges. So for example, that's a back edge. And you know when I go back up this way, because remember, I'm going to have no more incident edges to consider because they're all labeled, right? So I go back to D, and then I go this way. So I label this a discovery edge. I mark this, and then I would label this edge as a back edge because this endpoint is already marked. So the question I have for you is what structure are we looking at if you look at the black edges? The discovery or forward edges. What are those? Like what does that form? So what kind of graph, if I ignore the red edges, what would I call this? What is that? It's a tree, exactly. So notice the discovery edges form a tree, or discovery or forward edges form a tree. And that's always true, by the way, if you use DFS. And we call this a DFS tree. So if you use DFS, you get a tree that gets formed out of the forward edges, like this. Now keep in mind, if I started DFS at any other vertex, I get a different tree possibly. But there's going to be a tree. It's always a tree. And these DFS trees, we're also going to see that the other graph traversal algorithm also gives us a tree. They have different properties. So one that we've seen actually the other day was about cycle detection, for example. Notice that if this is a tree, notice that these discovery edges, you know how I told you how there's this way of justifying why there's a cycle, right? Well, this is exactly why. Do you remember there was one definition for a tree I gave you the other day that said that in a tree, there's a unique path between any two vertices, right? If I go from A to B, there's exactly one pathway that gets me there, right? Well, if there's a back edge that is incident on both endpoints of those ends of that path, I could form a cycle. This is actually why that works. The application I showed you last day works. Isn't that neat? So it's a very nice and simple idea, but but the big thing here is that DFS will, if they in fact are all part of the same connected component, or I apply DFS over and over again by bootstrapping it back from the beginning each time, but I do it at an unmarked vertex, I obtain something called a spanning subgraph. So what is that? It doesn't necessarily have to be connected. is a subgraph that contains all the vertices in the graph G. So it's just some subgraph H that contains all the vertices. So for example, you could say that the DFS tree in this case is a spanning subgraph because it has every single vertex in the graph in it. Now, if I were to just simply run DFS where I consider the entire graph, like I mentioned the other day, where I just restarted each time with an unmarked vertex, I could obtain a spanning subgraph regardless if it's connected or not. And each one of those connected components, when I run it on there, I'm going to get another DFS tree for each one. I'll get a DFS forest. Isn't that wild? So you might ask, okay, so there's this thing called the spanning subgraph. Okay, there's going to be a concept called the spanning tree. That's when the spanning subgraph is a tree. So for example, this is a tree, right? The black edges form a tree. We'd call this a spanning tree because it has all the vertices in the graph in it. So that's going to be relevant for when we start talking about a couple other graph theoretic problems after we finish talking about graph traversals. So are there any questions about this at all before I proceed to talk about our next graph traversal algorithm? But I will tell you that you can find all sorts of fun ways to use the DFS tree. I know sometimes I've seen people and talked to people that have used DFS trees in all sorts of applications, ranging from like bioinformatics to all sorts of things, where the graph represents some problem you're looking at. In that case, I think it was a string matching problem they were looking at, where they're looking for a specific kind of sequence, and they represent it as a graph, and the back edges represented something in their tree. There's a lot of ways you can think about these DFS trees. But if we're okay with this, I want to talk about the next graph traversal algorithm I want to show you. So are we okay with me proceeding to that? Because we're going to be going on an adventure. Okay, so let's head over here. So the next graph traversal algorithm I'm going to talk about is what we call breadth first search. And I want to explain it conceptually just like I did with depth first search. Maybe not with the same kind of story, but most certainly a concept that will be fun. So let's talk about breadth first search. So often I'll abbreviate breadth first search as BFS. And I want to draw a fun picture. So I want you to imagine that I'm like this great explorer out of something like Indiana Jones or something. Just try to imagine that. And I am in the middle of a jungle. And there's this temple I want to look for. It's filled with lots and lots of gummy candies. So it's a temple of gummy bears. We're not doing anything too disrespectful or anything. They want to share their candy with us, okay? They're being very friendly with us. And there's me over here in the jungle, and I have this place I would like to go to. It's called the Lost Temple of Awesome. It has some lovely, lovely gummy bears there. Some lovely, lovely gummy bears. They have giant gummy bears. So anyways, what I would like to do is I'm right here. And there's several different pathways I could take in this jungle to potentially find this lost temple of awesome, including some dead ends. That also includes some paths that really go off the beaten path here. So I don't know where I'm going. I just don't know. I'm sort of a fish out of water in this situation. So I'm going to go on a little bit of a journey. So I'm going to go on a journey here. Here we go. I'm going to go on a journey to find the Lost Temple of Awesome. Now, we talked about one way I could potentially do this if I imagine this like a graph, where I took these pathways and I formed, say, for example, a graph, using those edges to represent it. So one way we talked about it was I would just simply go as far as I can through the jungle, and eventually if I explore through all of these pathways, I could eventually find the Lost Temple of Awesome, right? Right? But here's the big but with this process. So remember, I used my thread and I tied up at where I start off, and I just simply go exploring as deep as I can. I go depth-wise for my exploration. There's sort of a problem with this approach if you think about it from this scenario, right? Conceivably speaking, I could go I could go on a little trip like this, then I could take this path all the way over here. Well, what if there's a jaguar over here? Or something like that. They just come right at me, yo. That's not a good thing. What I would like to do is be a bit more careful when I'm exploring the jungle. So keep in mind, theoretically speaking, it would get me to the Lost Temple of Awesome, but I might have to take a lot of different pathways to get there. So this brings me to the idea that we're going to use. We're going to search breadth-wise. So what I mean by this is, instead of using the thread like I was, where I unravel it and go exploring, instead what I do is, imagine I tie this string here right at my origin, and I measure out a number of steps that I would like to take. And what I do is I venture around every path I can take that is that one step. So I am doing a much more careful way of examining where I am. So what I mean by this is, I would, in my exploration, instead of trying to just go down one pathway, I would effectively take one step out. So let me just use a different marker just to illustrate what I mean by this. So imagine I take my string out and I lay out one extra step out, and I explore everything within that one step that is reachable from me. And then once I'm done doing that, I take another step. I explore everything within 2 steps of me that's reachable from the starting point. So at this stage, I'm effectively looking at something along the lines of venturing these 2 pathways. But every time I take a step, I explore more and more of the jungle, to some extent, from the beginning here. So as I'm doing this, I'm getting further and further along these 2 pathways. Note, I'm not like cutting past these over here. I would eventually have to take extra steps to go around that way. So the point is that I'm being much more careful now. I'm measuring out how far I go by taking steps. I'm going breadth-wise through the jungle by following the pathways. And eventually, if I take enough steps, my arm is only so long. Eventually, I'm going to take enough steps that if I keep following these pathways by going only these many steps away from where I started, I'm eventually going to get to the Lost Temple of Awesome. Smiley face. So this is the idea behind breadth first search, is instead of have it where I just kind of just run right into the jungle, which I would not recommend for a survival guide, is don't run directly head first into a jungle without like figuring out where you are. So some people would tell you, maybe we should spread out, maybe we should examine an area, like the next closest kilometer, see if there's anything nearby that we can see as a landmark, for example. That might be a little bit smarter. But yeah, usually running into a jungle blindly is not a good idea. Just an FYI. I haven't done it before, but if anybody has, they can definitely tell me all about it. But anyway, so this is going to be the idea behind breadth first search, is that instead of us going through the graph by simply going depth-wise in, I go breadth-wise. So this is going to have an interesting consequence in how a lot of the traversal properties that we had, like the DFS tree, how this changes based on how I explore. And the neatest part about this is that the heart of this process is all that I'm doing is I'm going to be switching out data structures. That's probably the weirdest part about it at first. When you hear this, it sounds like, oh yeah, no. It sounds like a very different process. They're actually very, very similar. It's just that I'm going to use a different data structure. You notice that DFS, at the heart of it, I was using something that looked like a stack, right? So in DFS, at the heart of it is where I do this exploration process where I examine my incident edges and I use a stack. Does anybody have any ideas of what might be the data structure I have in mind when I'm thinking about BFS? So I want you to think about the order in which you examine. So instead of thinking about it in terms of where I'm just going as far in as possible, then I back up. Instead, I want to imagine it like everything I explore, I'm going to examine those first. So not a hash table, not a hash table. Think about something similar to a stack. Something that's conceptually similar, but different. We're not going to need a priority queue, but that is, yes, a queue. Yes, a queue. In BFS, the primary data structure that's going to be hiding underneath this thing, in fact, you can explicitly use one, is a queue. So believe it or not, DFS and BFS are very similar. Just the difference is going to be how we're going to be exploring based on the underlying data structure. And in DFS, we use the stack. Like, for example, you can take the algorithm that I gave you, you can actually create your own stack and you can emulate everything I did with recursion, right? You could do the same thing with BFS. And in fact, in BFS here, we're going to use a queue. So I don't really need to do any of that fancy-pantsy recursion. So here we go. Anyways, with that being said, let's talk about this. So let's head over here and let's talk about what BFS is all about. So I have a question. Would you rather see an example or the pseudocode first? I don't care which order it is. We could do either. I'll tell you up front that BFS's pseudocode is quite similar to DFS's. So if you want to see the pseudocode first, we can do that and then do an example. Or do you want the example? Okay, maybe let's do the example. Okay, let's do the example then. So let's do an example. Let's do the example. I'm seeing lots and lots of people saying, yes, example, please. Give me that sweet, sweet, juicy example. So let's do that. Where's my marker? Let's use this one. Okay, so let's do an example here. So let's do an example of this whole idea. So let me just adapt it. So remember, I told you that there's going to be a queue involved in this process. So I'm going to just draw a queue off. Well, that's a little squeaky. So I'm going to have a front on the queue. Those are where I'm going to be performing my DQ operations. And then I'm going to have the rear where I'm going to have it where I do my NQ operations. Think of it just like you're going to get some coffee or something. So anyways, let me draw out a graph. Let's draw a graph here. So let's do a graph. So here's a graph. So I got 1, 2. I'm going to have an edge that connects 1 and 2. Then I'm going to have vertex 8, which is going to be adjacent to 2 and 1. I'm going to have vertex 4, which is going to be adjacent to 8 and 2. Then I'm going to have vertex 3, which is going to be adjacent only to 2 at this stage. I'm going to introduce vertex 5, which is going to be adjacent to 3 and 4. Then I'm going to have vertex 6 and vertex 7. Vertex 7 is going to be adjacent to 8, 4, and 6. And vertex 4 is going to be adjacent to... vertex 6 is going to be adjacent to vertex 4 and vertex 7. Now, one thing I would like to do is I would like to really emphasize the idea that there's sometimes trees buried inside of these traversals. So what I'm going to do is I'm going to introduce an attribute that's going to constitute the tree, kind of like when we talked about DFS. You know how I talked about the DFS tree? What if I gave you some way I could keep track of that information other than just labeling the edges? So I'm going to show you how I might do something like this as we do the example, and we'll see how this plays out in the pseudocode. So I'm going to create a parent. So suppose that I start my exploration at S, I'm going to presume that my parents of each one of these vertices is going to be null. I'm just going to write nil just to keep this simple for myself here. It's less letters by one. It's one letter less. So each one of these, when I eventually explore them, they're going to have a parent except for the root of the tree. Just like when I had a DFS tree, wherever I start, that'll be whatever you can think of as the root of the tree. So I'm just going to keep these along as we do the exploration in BFS, just because it keeps things a little bit tidy for me to tell you a couple interesting things we can do with these afterwards. So I'm just going to give each one of the vertices a parent attribute. And all of them are going to start off as null at the beginning. So, anyways, let's start. So, you know right away the first thing, because I'm going to start here. So I'm going to do BFS. So I'm doing BFS at S in this example, which is vertex 1. So 1's going to get NQ'd in first at the beginning of this process. Now, you might ask, Dan, what's going to happen with this marking business? You're going to still mark them. You're still going to mark them. But I'm going to mark them as I place them into the queue, because they're just going to be hanging out there anyways. So if ever I explore anything else a little bit later on, I most certainly want them marked just in case because I don't want them to go into the queue later, okay? So you're going to keep note of this. So when I start this process, I'm going to DQ1, and then I'm going to now consider all of my incident edges that aren't labeled yet. So notice that I have an incident edge here. So I'm going to label that edge as a discovery edge, just like I did before, or forward edge, whatever you'd like to call it. Either one's fine. And I encounter this one here. Now, notice that I've observed that this actually is adjacent to this vertex. I'm going to update its parent to be vertex 1. And I'm going to now place this into the queue. So I'm going to place 2 into the queue. And I'm going to mark this vertex because it is in the queue, because I've visited it. Now, next, I'm going to, remember, I'm not going to proceed to 2 yet. I have to go through all of my incident edges first. This is the first thing you'll notice, because I'm not going to go, remember, I'm not running into the jungle. Instead, now I'm being much more meticulous and I'm measuring out my steps. So I'm going to be counting this based on the number of edges that I explore. So notice that I'm going to be taking 1 edge step away from the origin. So this is me in the jungle. I'm going to take 1 edge out. So all the edges that are 1 away from me, I'm going to be considering. So now notice that I'm not done looking at all my incident edges here. So notice I have this edge here. So I'm going to label that as discovery. And then I'm going to have 8 here. Well, look, I have 8. I put that into the queue. I make sure to mark it. And since I have a new neighbor here I've discovered, I'm just going to label this parent to be 1. You're going to see how I'm going to use these parents in a moment, but I just wanted to kind of keep it along with us. So notice I've considered all the incident edges. They're all labeled, right? So now, what should I do? Any ideas what I should do next? I should do something maybe with that queue, right? What should I do? How do I continue this process? Any ideas? I'm happy to see any suggestions. Because remember, that queue is not empty yet, right? So if it's not empty, then most certainly there's still more to explore, right? But which one should I take on next? Well, think about it. It's a queue. So what operation should I do to the queue to get the next node I should explore, or vertex to explore? What operation should I use on the queue? You'll notice that when I started this process, I just simply dequeued out 1, and then I started playing around with it. So maybe, just maybe, what should I do? I want your thoughts about this, because remember, all I want to do is I want to take 1 step out, then 2 steps out away from the start. But really, remember, 2 here is just, It's one I have here, right? So all I'm going to do now is I'm just going to DQ2 now. And I'm going to DQ2, exactly. So let's DQ2. So now 2 is out of the queue, and I'm going to look at all of the incident edges. So now that's what I'm going to do next. So I'm going to start off by considering this edge, just for the sake of discussion. Now, one thing you should notice very quickly is that edge there, the opposing endpoint is already marked. Now, you might say, Dan, that means it's a back edge. But in BFS, we actually have a different name for these. So these edges, I'm going to color them green. These green edges that I'm going to color, these are called cross edges. Sorry, that's a little faint. Let me write that in black. So they're cross edges. So the green is cross edge. So we have discovery or forward edges, and we have cross edges. We're not going to have back edges in BFS. We're going to have cross edges. They have a different property. But anyways, I label that as a cross edge, but I most certainly am not going to NQ in 8 because it's already marked, right? So let's keep going. So next, suppose that I encounter, say, this one next. I'm going to label this a discovery edge. I'm going to NQ in 4. I mark it. I'm going to update its parent to be wherever I came from. In this case, it was 2. And then I'm going to keep going. Remember, I have to still consider all my incident edges. All the ones that aren't labeled, right? So now look, I have this one here. I found a new parent for my tree. And then I'm going to just simply mark, remember, I NQ in 3, I mark it. And then you might say, okay, Dan, I've considered, this is very awesome. I'm having a lot of fun with this. So if I am now doing this process again, what should I do next, everybody? I have considered all my incident edges on vertex 2, so I'm done with 2. So what's coming next? What's coming next? What am I going to do next? Yeah, I'm DQing 8. Exactly. 8's coming out. 8's coming out of the queue. It's 8's turn. Voila. So now I got 8's turn here. Well, this is labeled, that's labeled. This isn't labeled yet. However, I've already marked that vertex, so I'm going to label this as what kind of edge? What kind of edge is this? The edge with the endpoints 8 and 4. It's a cross edge. Yes, very good. So this is a cross edge. And then I have a discovery edge here, because I haven't yet explored. This one isn't marked yet, so I'm just going to update its parent, which I know it's 8. I'm going to put 7 in here. I'm going to mark it. And now I'm done with 8, right? So somebody tell me what I have to do next. What's next? What's next? DQ4. Yeah, exactly. See, are you starting to get the hang of this? It's very similar to DFS. Now we're just using a queue instead. And just notice the way I'm marking. So I mark it as soon as I uncover it. And I just have this cross edge business. Yeah, exactly. So now we got 4. So let's look at 4. So now that one's labeled. This one is not labeled yet, so I'm going to label that. So I'm going to label its parent to be 4. I'm going to put 5 into the queue. I'm starting to run out of space. I'm just about full, though. And then I'm going to mark 5. And then I go consider another one. Well, this one right here is a discovery edge. Let's take in 4 as the parent there. I'm going to NQ in 6. I need a little bit more space. I started running low on space here. There we go. If I got it in. I got it in, everybody. Okay, so now I've considered, oh, we missed one edge right here. This is a cross edge, right? Because its endpoint, its opposing endpoint is already marked. So we've considered all the incident edges on 4. We're done. What do we do next, everybody? What do we do next? DQ3. Yeah, exactly. So you're starting to get the idea of how this works out. So we're going to DQ3. Now I look at all my incident edges. I look for the ones that are unlabeled. So this one's already labeled, so I don't need to do anything here. This edge isn't labeled. However, this edge is already, sorry, this endpoint is already marked. So this is going to be a cross edge. And then I have considered all the ones for 3. I'm done with 3. So now I'm going to DQ out 7, right? So I look at all my edges. This one's labeled, that's labeled, this one isn't labeled. However, there's already this vertex that's marked. So that's a cross edge. We're done with 7. So now we got 5. 5's not very interesting, right? All of the edges are already labeled, right? So I don't have anything very interesting going on here. So 5 is gone. 6, all of the edges are already labeled, so 6 is gone. And notice that every edge is now labeled. Every vertex is marked. And we're done. That's BFS in a nutshell. Is that nice? So it's really just, it's very similar to the process we did with DFS, but just only main thing is the order in which we're marking them. We don't mark them when we start considering it. We mark it when we place it into the queue. And other than what, it's just a queue instead of a stack. That's it. Is that wild? So by doing this, we get a very different behavior, but it's actually underlying data structure is really what judges that, what causes that to happen. So this is an interesting example of how a stack and a queue can make a very big difference, is that you get 2 very different kinds of traversal methods. So you might ask, okay, so what do we do with this? So let's do the pseudocode for BFS, and then I'll come back over here and talk about a couple of things about BFS. So let's head over here. Let me write out the pseudocode. You're going to find that it's going to be quite similar to DFS, except now we have this just the 2 differences I talked about. So let's talk about BFS. So we got the algorithm. So we got algorithm. We got BFS. We give it a vertex U. This has a very similar setup to DFS does as well. So it has a very similar setup. So for example, if you want to do the same thing we talked about the other day, where you want to explore the entire graph, and if the graph is disconnected, you could start it up the exact same way I talked about with DFS. So it's nice that way. So it's just that we're just doing it in a somewhat different order. So we have vertex U, which is going to be a vertex of a graph. G is equal to VE. And the output, we call what we did here a BFS traversal. A BFS traversal of G starting at U. So, you know right away that you're going to have to create a queue at the beginning of this process because we use a queue. So we're going to start off by initializing an empty queue. So I'm going to call the queue Q. So I'm going to initialize an empty queue. And then I'm going to enqueue in U. Sorry, I'm going to go Q dot enqueue U. So I'm going to place U in, and then I'm going to mark it. So I'm going to mark U. Not you. I'm talking that U. So this is how I first get that initial setup, right? Where I put the starting vertex into the queue, and now this is where everything's going to start up. You're going to notice that we're going to keep doing this process until the queue is empty. So we're going to have a while loop. So while queue is not empty, we're going to do the following. Now, I might have to write the rest of the pseudocode up here. It's going to kind of go down, then back up here. So I'm going to be trying to be very careful the way I write this for you, because there's a lot of phrases. Okay, so I'm going to start off by, I'm going to do my DQ, right? Every time I consider if the queue is empty. If it isn't, then I DQ. So I'm going to do a DQ operation to get V. And then Now, I must stress that I'm going to write this in a way so that it's very easy to modify to solve other problems. So I'm going to throw a subroutine in here that I have no idea what it does. It just does some processing on the graph. So I'm just going to call that process. So process V, and I'll say do something. Do something to V. It just does something to V. I don't know. It could be that it visits it, it updates a counter, or something like that. That's what process is. I'm just going to assume that it's just some constant time process, but it could be something else. Now, I have to go through all of my incident edges, right? For every edge, VW, we're going to do the following. So, I consider all my incident edges, then I have to check if they're labeled or not, right? If they're not labeled, then we have to do something. So if VW is not labeled, then, so if VW is not labeled, then we need to check if it's marked or not, right? We need to check if, in our case, that W is marked, because that's the opposing endpoint. So I'm at V, I want to look at my opposing endpoints on each one of those edges. I want to see what the other endpoint looks like. So I need to see if it's marked or not. So if it is marked, so if W is marked, then what should I label the edge then as? Label VW as, what kind of edge should I label it as? So if I'm finding that the opposing endpoint's already marked when I'm exploring, it's a cross edge, exactly. Exactly, so all I do is I say it's a cross edge. So I label that edge as a cross edge. Otherwise, now, just to make this easier for us, because this is the last little bit of the algorithm, I'm going to throw it up here at the top. So this is going to start right below that if statement. So it's going to be after the if statement, we're going to have else. So else, so this would be the else for that if statement. So this if statement. So this is if W is not marked. So I'll just mention that W is not marked as a comment, just so we're making sure we don't lose track of anything. Now, you know it's going to be a discovery edge or forward edge. So you're going to label VW as discovery edge, right? You label that edge. Then you're going to NQ in W. So you're going to go Q dot NQ W. And then we're going to mark W. And then that's the end of the else statement. So this is the end of the else statement. This is the end of the outermost if statement. And then this is the end of the for loop. And then you have the end of the while loop. And that's it. So that's BFS, believe it or not. It's quite similar to DFS. It's just imagine if I spelled out everything in an iterative manner. This would be what it would look like if you took out and spelled out DFS, but you swapped it out with a stack, for example. But you have to be a bit careful about it. Typical in translation between iteration and recursion. You have to be careful. So there's just two things I want to point out in here. I talked about this whole business with the parents. I want to show you where those get set. So let me show you where those would get set. So all I'm going to do is I'm going to make two modifications. I'm going to label them in red. So u.parent, so the parent of u would be set to null right here before the while loop. And if you want to make it so it updates this parent each time, all you have to do is after you mark, all you do is you just set u.parent. This should be set to, sorry, my arrow is a little bit, it's pointing up. It's going to be set to v. So after you mark it, you can just set the parent of w to be v. So if you add these two lines in here, you actually can get all that information I talked about with the parents. You don't need it to make BFS work. It's just a special feature that you get if you want to get, like, say you want to form a parent-child relationship with all the nodes or vertices in the tree that we'll get after this process. So you could do the same. You could do something very similar to this with DFS, by the way. So you might ask, Dan, what's going on with all this stuff? Like what are we doing here? So the first thing I should talk about is the time complexity. So the first thing I should point out for you, I'm going to leave the analysis for you to take a look at, but it is going to end up being the exact same as we did with DFS for the time complexities. You might ask, Dan, why is that? Well, think about it. Conceptually speaking, all I did is I took a stack and I swapped it with a queue. Conceptually speaking, there's still some wrinkles to that. But most certainly, with a stack or a queue, you know those operations I do with like NQs and DQs versus a push and a pop, conceptually speaking, these can be all done in constant time, right? But if I'm doing effectively the same process again over, just it's spelled out in a more iterative manner like this, the time complexity doesn't differ. The only difference between the two that I gave you is one uses recursion, which uses like the call stack, and one just will simply just call this directly. But yeah, the analysis for this is the same as it is with DFS. So that means that when you have an adjacency matrix, the time complexity will be big theta of n squared. And for an adjacency list, the time complexity will be big theta of n plus m, just like we had with DFS. So I have the analyses for these in the notes. You'll find that the analysis is very similar to DFS. It's just the difference here is that you'll walk through this and you notice the counting is very similar. Just the difference is actually going to be in a couple spots. Actually, let me point these out for you. So let me just quickly point this stuff out for you. So one thing I want to point out to you, and I'm going to bring this up again when I start talking about a couple of the graph problems we're going to look at, is notice that this while loop is entirely dependent on the queue being not empty, right? But if I eventually dump every vertex that I could reach into this queue, you know that there's going to be some number of vertices I'm going to always have to consider at least one each time, right? But notice that each one of these has it for each edge here that's incident on it. Now, at first, you might be compelled to say, okay, well, it would be this, like the number of times this happens times this. But what we're going to see actually probably in the coming lecture is that the counting that we do for this analysis is a little bit more careful than just doing that. It's actually spread across the graph a little bit more carefully. I'll have a bit more of the details about this in the notes, but we'll all definitely be walking through it more carefully when we see how we can adapt BFS to solve some more problems, okay? But I just want to take note of this and plant a seed that there's something interesting going on with how we count the operations here with this nested loop here. So let's talk a bit about properties that BFS has. So let's head back over here. I want to kind of come back to this picture. Our picture of our graph here. So we talked about back edges, we talked about cross edges, right? You might want to know the difference between, like, why would you care about why we call one a cross edge and the other one a back edge? So I got to address this. So let's talk about that. There's actually something very interesting going on with this, with those black edges I have over there versus the green ones. So first, before anything, I should acknowledge what a back edge is. So in DFS, a back edge VW, so if I call it VW, that's the back edge, is where W is an ancestor. It's an ancestor. For some reason I can't spell today. Here we go. Ancestor is an ancestor of V in the DFS tree. So if you pull out the DFS tree, if you look at the back edge, there's actually this relationship that happens with the back edges. If you look at one of them, one has to be the ancestor of one of the opposing endpoints that's across on the other side of the back edge. So you might ask, okay, so that's what a back edge is. Like, what does it, like, that's one feature of a back edge. We talked about a couple things we could do with back edges. What about a cross edge? So in BFS, a cross edge VW is either, so I'm gonna plant a seed. I'm just being a farmer here today. I'm just planting seeds left and right. Maybe it's the hat. I don't know. Is either on the same level, which I'm going to define for you in a moment, on the same level as V, or it is on the next level. So I got to talk about what I mean by these levels. So you remember how I talked about how the black edges form a tree, right? That's what we said with DFS. In BFS, it's true as well. So notice that I have a tree. If I look at the black edges are discovery edges. So I want you to notice something that's very interesting that happens. If I start at S, you can ask a very interesting question about how many edges I use to get from one to another. So we can label each step I take in BFS. Remember, just like how I explored the jungle, I take one step in and I look all the way around me. This is corresponding to the number of edges I use to explore the graph. So each one of these forms a level in the tree. So notice that the parents of these are 1. So each of these, because it's the parent is 1, and that's its direct parent, right? That means that this is going to be using 1 edge to reach these. So I call that level 1. Where I start off, I'm at level 0. In fact, if you're really not compelled by what I'm doing so far, just imagine you tilt this sideways like this, and you imagine it like a rooted tree. So now I'm going to now look at this, and you say, okay, that one's parent is 8, 2, and 2. But each one of these, when I took that step towards here, well, this one was in level 1, right? So that means that all of these vertices that I just have right here, all of these are in level 2. So they need 2 edges to reach them. So this is an L2. This is the second level. So notice how many edges I have to use to reach them. 1, then 2. Anything I've just labeled in this blob or cloud here is, in fact, takes 2 edges to reach from S. Likewise, because the parent of this one is 4, well, 4 is right there. It's in the second level. This one's also in the second level. These last 2 are in the third level. It takes 3 edges to reach these from S in our tree. So if you follow backwards, if I ever wanted to, by the way, if ever I wanted to compute a pathway, if I wanted to compute a path from 5 back to 1 or 1 to 5, notice I could just follow the parents. So I could go follow the 4 goes to 2, 1, and there's a path right there. So do you see how these parents can be very useful for just tracing back through the graph to find a pathway? But it also has an interesting relationship. It forms levels just like when we talked about, say, binary search trees, when we talked about heaps, when we talked about trees, they all have levels, right? I have the definition of a level. The same thing applies here with my tree. But the tree has an interesting property that each one of these levels tells me how many edges it takes me to reach that vertex. So there's something interesting happening here with these cross edges. If you look at the cross edges, either they're on the same level as it's both of its endpoints, or it's on the next one. That's all I'm saying right here. So that's the relationship cross edges have with the rest of this tree. So now that being said, notice that these levels actually have a very interesting thing going on with them. So think about it. When I took that one step, why did I go to that vertex? It was because it was next to me, right? I took one step out and it was right there. So a very natural question I have for you is it just a coincidence that if I start at S and I go, for example, if I wanted to go to vertex 3, that the tree happens to make it so I have to use 2 edges. So if I want to go from 3 back to 1, I could follow its parents. So I had to use 1 edge, then 2 edges. Why did I do that? Is that like just a coincidence, or is that actually something that's highly ingrained in how I explored the graph? Is that just a coincidence, or is there actually something interesting going on here? So the question is, and I'll tell you, the answer is yes. This isn't actually a coincidence at all. What we're doing is we're actually computing shortest paths. So believe it or not, so I'm going to define a shortest path on an undirected, so-called unweighted graph. We'll talk more about weighted graphs next time. A shortest ST path consists of a least number of edges from S to T. So when I say shortest, I'm talking about the number of edges in it. So notice, so the big thing I want you to notice here is that whenever I go from one level to the next level, this corresponds to the order in which I dequeue the elements from my queue, right? Because each one of them was placed there when I took 1 step forward, then 2 steps forward, then 3 steps forward. If I look at any one of those as I did that 1 step, all of the number of edges I used at that one time had to have been the least number, because I was always walking 1 step uniformly across my graph. If you think of it like that, this isn't so strange if I told you that, in fact, that BFS is capable of computing shortest paths. So unlike DFS, which computes just paths, BFS, if you use BFS to compute a path in the manner I just described a moment ago, where, say, for example, you just did BFS, then boom, when you hit a node, like say if I'm looking at vertex 4, if I encounter vertex 4 and that's T, for example, if this was T, I could stop right here and I just follow the parents, right? I could just say, okay, go to 2, then go to 1, and there's my path, right? But this is the thing, BFS computes these. So that's one advantage that BFS has that I want you to know about. So BFS computes shortest paths. Isn't that neat? So if, and by the way, this tree with the black edges, that's what we call a BFS tree. So these black edges, they form what we call a BFS tree. So a BFS tree is simply the formation of the forward or discovery edges of a BFS traversal. And if you ever want to modify this tree to make it so you compute paths, yeah, you just hang on to these parents. It's really easy. It's actually really nice. So just, are there any questions about this before I kind of give a little summary before we wrap things up? Because we only got a couple more minutes here. Okay. So let me just summarize one last thing and then we're going to stop for today. Because I think it's actually a perfect place for me to stop. Because otherwise I would love to start talking about minimum spanning trees, that's going to be our next topic. But I want to make sure that I let you guys go appropriately. So let me just quickly summarize what I just talked about the last couple lectures, just in a little table. So the first thing I want to say is that traversals serve as the backbone the backbone. That's an E, by the way. Backbone for how we design algorithms for graphs. So just a quick summary just of things we talked about, because I want you to just be aware of things that BFS and DFS are capable of. Just to summarize all the applications we talked about. So first, if you want to compute a spanning forest or tree, or you want to check if the graph, or if you want to compute so-called connected components, so keep in mind, remember a BFS tree, DFS tree, these produce you spanning trees or forests. If it's a connected graph, it's a tree, a spanning tree. If it's disconnected, it's a spanning forest. But each one of these, you can actually identify what the connected components are as well. You can always store your tree, sorry, not the tree, you could store what you've labeled and marked in an additional data structure, and you could call that a connected component, for example. Say if you're using these for identification purposes. So you could use BFS and DFS both for these. Pathfinding. So pathfinding, you could use both of these. So pathfinding, you could do for both of these. Computing or detecting a cycle. So computing or detecting a cycle, you could use it for both of these. Remember, because of the way I talked about cycles, cross edges, you could also use those to identify cycles as well, just like a back edge. And lastly, shortest paths. So the last one, shortest path. No, you can't use DFS for this, but you could use it for BFS. You can compute a shortest path. So we're going to see much more further generalizations on the concept of a shortest path in the coming lectures. Once we start introducing where we have the edges having weights or costs on them. But yeah, so this is everything I have to say about graph traversals. I think this is the perfect place for us to stop. And that being said, I want to thank you very much and have yourself a beautiful day. I'll see you later.